All right, let's talk a little bit about buffers. Buffers are probably the key thing to kind of start chapter 17. And again, chapter 17, really not part of the AP anymore. It used to be really a big crux of the course. Very important, a lot of math, a lot of titration stuff going on, but of course not in 2020. So the idea of a buffer is simply that it's a mixture of conjugates. So any conjugate pair and that conjugate pair, as it turns out, resists changes in pH. And we'll talk about how it does that today a little bit, and we'll talk a little bit about some of the related ideas. Again, I know it's not on the AP test, but this is really important stuff that you should know as a student of chemistry, and so we'll kind of go into it a little bit. The first thing really is simply how it works. Let's say that we have the example of a mixture of, and it doesn't matter the amounts. Let's say that we have a mixture of HCN and NaCN, where again, we don't need to worry about the Na part of NaCN. So we have our conjugates, HCN and CN minus. The idea is that, of course, HCN is a weak acid, CN minus is its conjugate base, and because they can perform those functions, additions of strong acid or base are going to be affected by those two things in a way that's actually going to limit the effect that the strong acid or strong base could have on changing the pH. Normally, you would think if I had a lot of a strong acid, the pH would go way down. If I had a lot of strong base, the pH would go way up. That's not the case when you have a buffer. And we'll talk sort of about why that is. It's a good precursor to talking a little bit about how titrations work. But I think we're a little bit a ways from titrations. That's certainly the next day's topic. And then we'll have one more topic on chapter 17, and that'll kind of do it for chapter 17. And then we'll spend a day or two on each of chapters 19 and 20. That'll put us into early April, and we still have a month or so. If we decide that we want to go forward to the AP, we'll push forward at that point and focus a little bit more on review. Probably by then we'll know more from the College Board on what exactly we're reviewing for. But back to the matter at hand. So if I add a strong acid, we just are going to call that H+. When I add that strong acid, which of the two parts of this buffer system would react with it? Well, understandably, it should be the part that has the opposite of the positive charge, and it's going to be Cn minus. So Cn minus responds, and it responds by sticking to H+. And when it sticks to H+, it turns the H+ into HCN. And so essentially what we've done is a very strong acid, H+, has been converted into a very weak one. And because we've converted an incredibly strong acid into an incredibly weak one, the effects on pH are certainly minimized. There's almost no change in pH because this really strong acid that would really lower the pH isn't there anymore. Instead, what we have is HCN, which barely even produces any H+ at all. If we have the opposite situation and we add a strong base, let's say OH minus, of course, a nice quintessential strong base. Well, what part is going to respond to that? Well, of course, we already used Cn minus, so HCN is what's going to respond. And the response is not quite as clear, perhaps, and it's a little bit more complicated than we're going to make it in this case, but the way it responds is simply you're adding an acid and a base together, the H and the OH here. If we want to consider it this way, it's not 100% this way, but this is functionally good enough. They're going to turn into water, and then it leaves you Cn minus. So they make H2O, and Cn minus. And so again, what we've done is take a very strong base, OH minus, and convert it to a very weak one, Cn minus. So a very strong base, OH minus, is converted to a very weak one. Cn minus. And so again, very little change in pH because we've taken something very, very strong, OH minus, and replaced it with something very weak, Cn minus. There are 3 related topics to this that are just good to know the terms and the ideas, but again, no longer important from a College Board perspective. But if you're taking the subject test, I don't know if they're going to offer that anymore, or you're in a college class in a year or two, you probably want to know these kinds of things. So I think they're all pretty approachable. The first related idea is called buffer capacity. Buffer capacity is simply that the buffer can prevent changes in pH as long as its moles hold out. So the buffer can resist pH changes until that didn't look right. Until its moles run out. So either the moles of the HCN or the CN minus in this particular case, but when one of those moles runs out, of course, it could no longer replace the strong acid or base with a weak one, and so at that point the buffer sort of is broken and no longer functions, and the pH will shoot upwards or downwards depending on what you've added. So there's sort of a limit to how much the buffer can do, which I think is probably pretty sensible. There's another concept or two as well. One is called an optimal buffer capacity. And optimal buffer capacity is simply that you have equal numbers of moles of the 2 parts of the conjugates. And that means that it can respond to either an acid or a base equally. So, and that's kind of a related idea to the last concept, which is simply that you can design a buffer to have almost any pH you want. The idea simply is that I can adjust the amounts of HCN and CN minus, or whatever conjugates I have, and because I can adjust those in any way I want. If I add more HCN, I can make the pH a little lower. If I have more CN minus, I can make the pH a little higher. And you can choose your conjugate pair wisely and make a buffer to be pH 3, 4, 5, 9, 7.75, whatever you like. And so because you can do that, you can design a buffer to match the environment that you want to run a reaction, and certain reactions function better at certain pHs. Certainly that's true of a lot of living systems, a lot of ecosystems. Certainly within a lot of organisms, our bodies function very well within a very narrow range of pHs, and we have a lot of buffering systems to keep it that way. And so those systems work. Again, if you go back to the Ka expression or the Kb expression, the relationship of the ratio between the HCN and CN minus or any of the 2 conjugates, those have a lot of impact on the H3O plus or OH minus concentration, and so you can design your buffer to do that. And the optimal buffer capacity, which we mentioned just a moment ago, because those 2 things are equal, they divide out, and the pH or the pOH is directly related to the H3O plus or OH minus concentration. So that's why they're called the optimal buffer, because you can sort of design them very easily to have a very specific pH. I think that's enough for what we need to worry about buffers right now. We may talk about them again when we talk about titration curves, but that is a topic for another day.